Computer vision in your pocket. My goal with this is, I think LLMs kind of stink. They're interesting, they're great, they're awesome, and at the same time they really stink, and I think they're overhyped, especially right now. There is an area of machine learning that is actually, if you actually want to make money with computer vision, with AI, which is not AI, I would say you should look at computer vision. There's a lot more that you can do, and you can actually make real money right now doing it, or real good use cases with it. So this is actually a way of introducing you to that stuff via something that's, I think, accessible to a lot of people, which is the phones that come off of the pictures that come off of your camera on your phone, right? This is not, I'm not going to have anything fancy in terms of the images I'm working with. These aren't technically off, the pictures I'm going to show you aren't technically off of my phone. They're technically from my bigger cameras that I did. This whole project started for me because I like doing photography, because most of us here probably do as one of our hyperfixations or hobbies. And I wanted a better way to look at what my pictures had and what it was telling me, like finding the pictures I actually cared about rather than all the garbage. That link at the bottom, which I will repeat at the end, is this slide deck. Okay? So you can take a picture now, or you can wait until the end and take a picture at the end. If you decide you want to save the bits. That's me, I'm Steve. If you couldn't tell, I'm a very informal speaker. I want questions while I'm giving the talk, not at the end of the talk, please. Chances are, if you don't understand something, there's about 5 or 6 other people in the audience at least who don't understand it, and I'd rather catch it then. This is the GitHub repo for today. Not all the code examples got done in time. I'm, again, ADHD overambitious. So there's a bunch of code in there, but not all of it's filled in. I'll be filling that in over time, and you'll see the exact code I'm using today. And I made the repo in such a way that once you've loaded the pictures up, everything else you do from that point on is generic. So getting your pictures in is the thing that you'll have to do with yours, but it's pretty easy. So the goals for today are teach you some very basic ideas in computer vision and transformers. And like I said in the beginning, we'll ask again now, how many people here have actually worked with computer vision, done stuff with computer vision? Yeah, that's what I figured, a few. And one guy claims he's an expert, or he's done a lot, so he's going to be my truth teller. I want you to get hands-on in the sense of like actually seeing it done, with seeing some of the stuff you can pull out some of your photos. And I would hope we're going to have some fun along the way, because if nothing else, I don't want you to fall asleep, right? So that happens a lot in talks. So the goal is not to have you fall asleep in the talk. So first things first, let's get going with the real stuff. Embeddings. Have you guys heard of embeddings at least today? Does everybody have heard the term at least? Yes? Do you understand what an embedding is? Okay, so that's what I figured. Most people are shaking their head no. I'm sure there's people who would shake their head yes. You can check your email, but no YouTube videos, please. So embeddings are handling a problem of turning things into numbers. That is what an embedding is all about. I'm giving you some motivation for why we need it with it. You're going to start with unstructured data. And unstructured data is challenging for computers. What's an example of unstructured data? Pictures. That's too easy. What's another unstructured data? File system. Yeah, that is, but it's kind of whatever. Yes?
So if you have like a keep track of certain species, take a picture like every hour at an interval in many directions, and then you have like 10,000 photos, but then you have to...
Right, so pictures, like, we're talking about pictures, lots of pictures. Text, right? You should know unstructured data is lots of text. Like, we're fine with a sentence or a couple words, but if I take a book, there's no structure in the book except there's a bunch of words in it, right? What's another example? Audio files, yeah. Would someone say speech? Is that what someone just said? Good call. Audio files. There's a lot of data in there, but it's not structured. It's not easy for a computer. So like, for example, if I tell a computer is 2 less than 3, the computer says, I know what to do with that. That's great. I'll flip some bits because some OS guy or some low-level guy figured out, or gal figured out how to do that. But if I say, is this kitten less than this kitten? Or is this kitten cuter than this kitten? Or anything like that, the computer has no idea what to do with that. Or are these 2 cats? Right? About the only thing computers can do really with images natively is, are they exactly the same? And if not exactly the same, where are the bits different between them? That's about all a computer can. To a computer, a picture is a big array of numbers and has no information in it other than the numbers that you see. And so our problem is how do we get the computer to actually be able to tell us something about these pictures, unstructured data. So this applies, all the stuff I'm going to talk about with the embeddings and stuff, this applies to text, all that LLM stuff as well, and embeddings from text. So the answer is neural networks to the rescue, right? And so what ends up happening is, to create an embedding, what you do is you take your matrix of numbers, or whatever it is, like in this case a picture of a kitten, you put it through the neural network, a deep one in particular, usually, yes, deep one, and what comes out the other end is an array of numbers. Okay, so you're like, great, I got an array of numbers. That array of numbers, the neural network is supposed to learn features inside of that image, and that array of numbers is supposed to encode some sort of information about those features in that picture. Does that make sense? Those numbers typically tend to be floats. Even though I put a whole bunch of ones in here, they typically tend to be between -1 and +1, is usually what I've seen. They can be stuff like this. They can also be integers. That's a whole other discussion. We won't go into that today. But just think of it as there's an array of numbers, and it's going to tell you that number encodes stuff about what's inside of it. What's another thing that we do like this with unstructured data? This is a Linux group, so you guys, I'm from New York. So when we use guys, it's gender neutral. When we use it amongst ourselves, so I'm sorry, I try to work on folks. So you folks, what's another way that in Linux, what do? What's another example of this? It's really simple. You do it all the time. When you download a package, they tell you even though you're supposed to and you never do it, but what are you supposed to compare? The hash, right? The MD5 hash. An MD5 hash is the same thing as an encoding. I've taken some big unstructured data, and I've turned it into an array, a string, of numbers that says something about that. Right? That's an encoding process. How many of you work in geo? Does anybody here work in geo stuff? Nobody? Yes? You do? Okay, now you're on the spot. You shouldn't raise your hand. Okay, so in geo, what's the process where we take some unstructured data and turn it into a two-dimensional vector? Yes. So he's basically saying geocoding. Have any of you done geocoding in any of your little map apps or anything like that? I have an address. Hey, Ryan. Sorry, Ryan and I used to work together a long time ago, and I didn't notice he was here. So, and Ryan has used my app that does that kind of stuff as well. So geocoding is the process of taking an address and turning it into 2D coordinates on a map. Right? A computer, if I said whatever the address of this is in Pasadena, California, and I feed that into a computer and I said, where is this on the map? Natively, it can't do anything with that. So geocoding is a process of putting some unstructured data, an address, and turning it into coordinates. These are all examples of ways. In this, we have a particular one, which is the neural networks. We good? We're going to go over this more. You don't have to totally get this yet. There'll be more talk about it, all right? So this is the part where I'm going to teach you some computer vision about actually what's going on under the hoods. Have you guys heard about those embeddings with text? Were you at the RAG talks? Any of the RAG talks have to talk about that. Because you need embeddings to do RAG, retrieval augmented generation. Right? So what's actually going on under the hoods with this is, and this is particular to computer vision. Remember I said there's a neural network. So you feed it, I'm supposed to stand here, but they can't control me. So is this a pointer? Yeah. So what you do is you start with your image and you feed it into the first layer of the network. Right? And then that network, and everybody understands basically what's happening at the most basic level. Each one of these nodes in the neural network is a nonlinear regression equation. Does everybody know that? Yeah? No? I see two heads. No, you didn't know that. Good. This is really, really important, especially for all this LLM bullshit about how this is intelligence and it's a hallucination, and it's none of that. This is a bunch of regression equations here, and we're going to be basically fitting those regression equations through some sort of fancy math to give us the output that we want. And so what's a hallucination in real life? It's an error. These are predictive models. It made a prediction error. That's all it is. Yeah.
In convolution neural network, you are doing activation
Yeah. At the end, I'll show you. We're getting there. You jumped the gun. You jumped the gun. Hold on. So what's happening? I'll get to that one. Ready? So the image goes in as all this. We start going through the layers. And typically when we do a prediction, what comes out at this last layer is our predictions. Right? At the last layer, this would be like, this might be something like woman, cat, dog. Like what's the weightings on those? And tell me what the thing is that I've actually got coming out. Usually what an embedding is, you drop this, and you just give the output of this last layer. The numbers that, you might do some standardizations on it and stuff, but it's basically the numbers that come out of this last layer in the network. You skip the last level of the neural network, and you just say, just give me the numbers. Give me the numbers here. So the number of nodes in that final layer of your network is generally the number of numbers in your output vector. Okay, does that make sense? And why is that thing important? Well, so here's what's happening as we move through the layers. For vision, I don't know, I think on text it's much more black box. As we move through, here's what's happening. At the very beginning layers, the network is going to start picking up on like really basic features in the image. Have any of you done photography or image stuff and run filters over your images, like an edge detection or any of that stuff? And you always have to pick like a whole bunch of things, like what's the size of the kernel, all that other stuff when you're doing that. The neural network is learning that on its own in that first couple of layers. And it starts picking up on significant features like lines, color gradients, things like this that are different between your different images. Then as it moves, those features become the inputs to the next layer. So that next layer can start putting things together. So in this case, it's starting to put things together like eyes. Right? It's starting to put together features that it will find in the images of this face that are conglomerations of, edge detections and stuff like that. And as we keep going, it's putting together more and more layers of that image. And so by the time we get towards the last layer, we're starting to put together faces. Right? And that's just if you were doing like a face detection algorithm or telling people apart algorithm. Right? But this is a simplistic way of understanding it in a case I think everybody understands. Does that make sense? So as you move through the network, you're actually starting to put more and more features together to get to the things you want to predict. And so that's what's happening when you're teaching this network. You're telling it, start finding the features here that are most important along the way to getting to the prediction I want. And so it gets really good at those things. Does that make sense? So what should happen at the end is this embedding layer has captured the features that are most important that we were using to do predictions with. So those numbers represent how well are we putting together those kinds of features. So that's what it means when it's extracting features from the images. Does that make sense? You can get embeddings from any of these layers you wanted to, right? You just have to basically say, don't go to the next layers, just give me this. Does everybody know what fine-tuning does? Do you know what fine-tuning is?
Adjusting the weights.
Yeah, and there's lots of different ways to do it. But so this is what they say when they're fine-tuning. You get some big foundational model where they gave you the weights, which was very nice of them. They don't have to do that. But they gave you this whole neural network. They give you the weights for it. And basically what you do, you chop off this last layer of their network that does the predictions, and you recreate a bunch of new nodes here and get all of this stuff to start predicting your nodes. Right? Like if this was like, say, like a dog training data set and you could chop this off, put a whole bunch of different cat classes to predict really well at cats. And it would keep all of this information that it had learned about putting features. I think this is everybody kind of wants to understand these terms. Is that should I keep doing this kind of stuff? Is it helpful for people in the audience? Okay, good. Yes. Excellent. You win a prize and a medal because you asked a question and you're the first person. Go. Oh, yeah, right, he did. Sorry.
So are you saying that the embeddings are the last layer or all the layers?
No, typically, the embeddings are the output from only the last layer. Because all of these layers go into making up this layer.
Because we are assuming that the weights on that last layer is the best.
Yeah, what you're assuming is the pathways all the way through make it such that the number that comes out of this last layer is the best at predicting what you want. So you don't actually need all the other weights coming out, the outputs from all these other ones, because they all get put together at this last layer. Does that make sense? Yes, the outputs, not the weights. The weights are just how we translate numbers into another number. What we want is the output from that last layer. Yeah, so he's bringing up that is forward and backward data going backward. Yes, that's all part of training. We're not going to talk about that. Let that wash over you. Training, when you're training this, data goes all over the place. It's a lot more complicated. This is one of the reasons why, can I give an LLM thing for a second? Okay, this is why when I tell people when they start with LLMs, start with RAG rather than starting with fine-tuning. And the reason is, to do RAG, you just pick a model, you get the embeddings out, and then you do some similarity search. It's very easy, as you'll see today, to calculate embeddings. To fine-tune, you actually have to have like the same infrastructure and the same kind of knowledge in place that went into training the entire model. Because what you're going to do is train this neural network on a new layer. Right? So if you're just getting started, don't start with fine-tuning, is my guess, to see if your problem even works. Okay? That was an aside. Are you ready? Next slide. Are we good? Okay. And so this is me talking more a little bit about where the embeddings come from. Right? So there's the puppy. We do a whole bunch of final stuff. There's the last layer. We drop the class probabilities, and we just take this last layer's outputs instead. That's the embedding. Okay? Everybody pretty clear on that concept? Okay. So embeddings are used all over the place, and I think they should be used more. So then what happens is, so you're saying, okay, great, I got this vector of number. What does that number vector actually represent? That number represents the features in that image, right? I'm doing it here in 2D, but if you have like a 5 to 12 dimension, like you've heard of the vectors that come out of like a 512 or 1024 in length, those are the coordinates in a 512 dimensional space. Visualize that. That's why I made it 2D, right? But basically what that's saying is each one of those numbers is a coordinate. And if your model has been trained well on data that fits well to your use case, coordinates that are closer together should be similar images to the images that have coordinates which are farther apart. And that's a big if, though. And I didn't get that part of the demo running because it was some cutting-edge code that my coworker couldn't get working for me. But there's two parts that go into this, and I'll talk about this in a second. There's the model, and that's what everybody seems to get excited about, right? Like, when you read about, oh, I got better performance, and you go look at this model's better performance, and it's like 0.5 better performance or something like that. And then there's also the data that went into training that model. And it turns out that the data going into training the model can have a much bigger impact than the model and the architecture that you choose. There's a whole other talk I give, but basically you can take 10% of the data, duplicate it, and your model will get like 50% performance compared to what it got before. So you could put a whole bunch more parameters on, you can get those fancy GPUs, you could train it forever, and it's still not going to do any better. So, which is why if you listen to a bunch of podcasts about this stuff and then people say, oh, should I get a bigger model, or should I, if I had $1 to spend, should I spend it on a bigger model, or should I spend it on cleaning my data? They always say clean your data. Good quality data, I mean, how many of you took some sort of statistics? You all took it, right? And what did your statistics professor tell you about the quality of data? Garbage in equals garbage out. And that hasn't changed because remember, we're just doing a whole bunch of regression equations. So you can put as many parameters on there as you want. If you're feeding in garbage data, you're not going to get good results. I was training a satellite model the other day, image processing with garbage data, and the model, its learning plateaued at like 0.1, when it should be at like 1 is what you're going for. And that's because the data was garbage. So pay a lot of attention to your data. All right, so this is a whole thing to say, hey, things which are more similar should be closer in this coordinate space. Does that make sense? And that's how RAG works as well. Sorry that I'm going off image stuff again, but that's how RAG works. What you do is you make embeddings for all of the documents that you have, And no matter what, data going into an embedding model, it always stays the same. If you put the same data through, it never changes. You always get the same embedding out, right? And so what you do is you make embeddings for all of your data, you get the user's query, you embed the user's query with that exact same model. Does that make sense what I just said to people? So you have an embedding model, you've embedded all your data, put it into a database using that embedding model. Clear? Your user asks a query saying, hey, usually you that query straight onto OpenAI and say, hey, OpenAI, or whatever you use, or Claude or Llama or whatever you're using, give me the answer to this. Instead, what we do now is we say, take that user query, run it through the exact same embedding model, now search the database, find all the stuff that I have that OpenAI doesn't have or Claude doesn't have or whatever, add that into the user's query as context for the LLM. So that what you've done is you've said, here's the original, and then send that on to the last model. And you're saying, so here's all the stuff, here's the user's query, and hey, for context, here's all the stuff that I know about that question, so you can restrain your answer to that. That's RAG in a nutshell. Good? Sorry, was that good? You liked it? Thank you. Even though it's not computer vision, I hate how much people are like glorifying LLMs and like RAG and making it like this. If you're not in the ivory tower and you're not super smart, you don't know you can't do this at all. And it has nothing to do with smartness. Okay, so then the question is, I'm going to show you some pictures actually of embeddings in 2D space. These are like 512 dimensional vectors. In one case, it's like 2K dimensional vectors, but I'm going to reduce them to 2-dimensional space. Because can you see in more than 3 dimensions? Like, can you visualize that in your head? Can you understand it? I can't. 4D, I kind of can. You can take a cube and kind of move it through space, but that's about it, right? And so we need some way to actually make it decipherable to us to see how things are close. And so there's a bunch of different ways. A bunch of you said you took stats. Does anyone remember principal components analysis from stats? You do? You don't? Shame. Did you learn about it at one time, though, and you forgot it? Dude, we're about the same age. I did PCA out the wazoo. So what PCA is a dimension reduction technique. You have like a table of data is usually what you had, some sort of spreadsheet or something of data, and you wanted to have less dimensions to put in your regression model and you didn't care about explainability. What PCA does is it takes that cloud of data and it straight linear algebra. This is not a statistical technique. This is straight linear algebra. You just basically take the eigenvalues and the eigenvectors. Everybody remembers those exactly, right? Totally. And then what you do, basically what it's doing is it finds, in this cloud of data, what it did is it found PC1, principal component 1, is an axis that captures the maximum amount of variation in that data. Does that make sense? And then it says, okay, given that, I now need to make an orthogonal vector relative to that captures the next most amount. And so that's what it's doing here. And then what you end up is you can replot into this new principal component space, and you've only got 2 dimensions rather than 3. And it's trying to maximize variation captured among the 2. So its goal is maximize variation. What we're going to be using today is something called UMAP. I still don't understand it exactly. It involves fuzzy logic and Riemann topological operators. Everybody's worked with those, right? So, but basically what the idea is it's trying to do is it takes the multidimensional space and it tries to, as it's bringing it down in dimensions, it's actually doing model fitting. This is not a linear algebraic technique. This is actually a model fitting technique. And what it's trying to maximize is keeping closer things close together as it reduces the number of dimensions. Okay? And that's what we're going to be seeing today. It does way better at for embeddings than PCA does, because it's actually like aware of the data and trying to keep things in a certain relationship. Okay? I don't think most people need to know this. I just wanted you to kind of understand it at a very high level. The important part about this, though, is that changing the data set, either the samples in the set or any of the values, will change the coordinates. So while I said embeddings doesn't matter, no matter what, the embedding will always be the same if you put it through. The coordinates will not be the same after this if you change anything about the data set. You have to rerun the coordinates if you change anything in the data. That was the big take-home message. Okay? Embeddings stay the same unless you change the model. 2D projections are sensitive things. All right? That's it for slides for now. Everybody good? You want more talk? Sure. No. Everybody's starting to be like, okay, that's enough. Let's just show me something interesting. All right. So let's see. Okay. This. Yeah.
When you do the PCA, you take the covariant matrix and diagonalize. But when you do the UMAP,
UMAP is not even anything like that. It's PC. So the question was, when I interrupted, he didn't get all the way to his question, but I think his question is going to be, PCA is like a matrix manipulation technique. Is that the same thing in UMAP? And the answer is no. UMAP is a statistical fitting technique. You're doing gradient descents and all sorts of stuff as you're trying to find the right coordinates, okay? Quick geo thing though is, what's another place where we do that kind of dimension reduction in geo? Kinda, you gotta be a little bit more specific to get credit for that one. Not exactly. Okay, what shape is the Earth? Spheroid. Ugh. It's a spheroid, it's not a sphere, but it's a spheroid. And what shape is a map? Flat, 2D. So when we create a map, we are projecting from 3 dimensions down to 2 dimensions, exactly like that. In the case of maps, it's formulas, not statistical fitting. And that's all those different maps. Trivia, cocktail party, people love it. All right. So for most of the stuff I'm going to do today, I'm going to use the visualizing from the company that I work for now. But I love this stuff, even before I joined there. And like the hard part for me of working with this stuff is not playing with the data all the time, just because it makes it so much easier. So what we did, the example 1, I'm not even going to walk you through it. But example 1, when you go to the source code repository, actually just loads your data into the platform. And so the only thing I'll show you here is, because some people will give me quizzical looks, fine, I'll show some of it. You give it a directory, and you make a data set from that directory. And the data set is the thing that we work with, right? And it's like 3 lines of code. And in this case, there's 2 examples I gave you. One is, if you don't care about any of the metadata in your images, you just like, give me all the images and put them in the data set, that's fine. For me, because remember I said this was my photo collection, I actually wanted to see if I could do stuff with EXIF data. Does everybody know what EXIF data is? Is that metadata associated to images? So the second example actually shows extracting the EXIF data from the image using EXIF something, and then attaching that to the sample inside the data set. Okay, so when you go back, that's what you're going back and you're looking at. We don't have to talk about that part. Everything from here, so remember I said it was generic? Everything from here on just assumes you have a data set. You don't have to do anything else. A data set of images. Good? Okay, so nobody said no, so I'm assuming the answer is yes. That's what I tell my kids. Not that you're my kids. Yeah?
You're feeding the same neural network to EXIF data and the image data?
This has nothing to do with neural networks yet. Okay. Good question. Did anybody else have that problem? Yes. See, his heads are shaking. This is exactly why you should ask questions. This is just loading the data set into the platform. We haven't done any fancy machine learning yet.
So you're loading the EXIF data because you're going to be using it.
And it turns out I don't.
Okay.
But I left it in here as an example in case people wanted to do something with their own images. I could have, for this case, this 1-liner or this 2-liner would have been enough. Just take.
You're wasting our time. You're wasting our time.
I'm sorry. I know your time is precious. All right. So the first thing that we can do, and I don't know how many of you have done this, but I need to make this bigger. Oh, come on. Which one is it? There it is. Can you see it in the back now? Good? Okay. So we have these things. We have things called plugins, and some dude wrote a plugin. In this case, it is a dude. He wrote a plugin that actually computes problems with images. Just things that I always want to see that I can never get out of, like Darktable and things like that, which is things like, is the brightness off? Is it blurry? Although the Laplacian filter is terrible for that. But like salt and pepper and things like that. So once I've computed these statistics, I just say, hey, go compute these statistics. That's what's happening. I load this, I say compute it, and it automatically gets associated with my data set, and then where's my data set? It was supposed to have launched. Where'd it go? Sorry, you can't see this part. I forgot to start my Mongo and Postgres instances. And what am I using? I know I'm using Docker, but I'm on Ubuntu, so I would have rather used Podman. Docker, start, photo, or Mongo, and then, but the beauty is, with containers, it's super fast. All right. Now I can start up the platform. Sorry about that. So I'm launching the app part of it right now. He hates that I'm using Docker and not Podman, and so he's leaving now. He goes, oh, you do? Yeah, great. Yeah. We don't need no daemons. And of course, it's running a lot slower now. 51 is the platform that we do. It's you pip install it, and then it's got like a bunch of... I don't know why it's not loading, which is not fun for me. Because it was working. This is what I get for rebooting my machine. Yes, I did. I know it doesn't matter. It shouldn't matter. I don't know what it's doing. Hold on, let me try one more time. I know, exactly. This is the excitement and the horror. Yeah, it just did this before, too. Rats. It didn't shut down when I just told it to shut down, or it's doing something weird. And it just did it before, and I don't know how to get it to stop. And I did this, for those who are here, we're at Linux, so I can do ps-sauxw 50, and then I grep for 51. And you can see, oh, there it is. It's bound on that port. So and then I say, actually, I should do this. Kill -9, but I'm a little worried about this because I don't know if it has a lock file somewhere or something. 108.92, right? And then you would think, I do this, and it should work. What's that? Am I using the right? There's no virtual environment. This is just all running right here. And I don't know, I've rebooted to exactly get rid of this problem, and I don't know why it's not happening. So let's see if we can start it another way. You're like, this is a great demo, Steve. This is a ton of fun, thanks. Import 51 as foo. fo.launch app. Did I spell it wrong? Yes. Pair programming prize for you. And it's probably going to give me the same error, but... Anybody have any other ideas about how I can kill that connection to that socket? How do you grep for, is it LSFOF that tells you sockets? Wait, I'll take his because he's closer. Nope, here, go. Netstat-AMP. Could I grep for 50? Oh, this is the best part of the show. He installed Netstat live. I don't know. It was working. I shouldn't have rebooted. Just too much. Just app install. Did I put get? Now I'm. Oh, so you sent me down the wrong path. It's all your fault. Did you? Is that what you said to start with? They said the wired network here is fine. In the meantime, any other suggestions about how to kill that thing? SS-T-U. How about grep? No? Grep 5150. That's where it's going to be. Maybe it's dead now. There's no way I'm going to be able to look. Oh, there it is, 5151. All right, how do I kill that? I don't want that anymore. That's the problem right there. These two. These three. I don't know. So reboot. Control Alt Delete. What? The 5151. All right. LSOF. Just like that. Dash A. That's a good idea. And grab 5151. No. Okay. This is like turned into the Linux contest. You thought you were going to learn about computer vision. That's not helpful. Why is it taking so long? Do I need to be sudo? Oh, there it goes. So it's all, this is the one I need to, oh no, that's not the one I need to kill. That's the one I need to kill. Is that right? What? Kill -9. 10936. Like that? Yes? Linux? Yes. Good. If it doesn't work, it's your fault. All right, here we go. Yeah, I killed that. Yeah, but that doesn't. Don't clap yet. We'll try again. I'm thinking there's something stuck somewhere. 51 app launch. Not lunch. Launch. Photo album. Well, I said I wanted us to have fun. Isn't this fun? No. That's good. I'm not touching anything. Why isn't it? That's bad. It's taking too long. No, I just did that and it didn't fix it. Then I'm screwed. No, we're screwed. It's just all screwed. Now I'm trying to think of how I'm going to rescue this demo. What? No, I'm using the local network, but it's all running locally. Maybe if I unplug from the network. What? I know, but maybe you never know. It's Ubuntu. Take localhost down. I'm unplugging. That's going to totally fix it. Didn't fix a thing. Yeah. It's not, Something's going on. Something's lost, logged, corrupted. What? It's still loading? It shouldn't take that. That's like one of those things when it takes that long to load. It's probably listening. Yeah, I do now. Because some great guy told me to do it. What, sudo netcat what? Localhost space, and he's blah, 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 blah. What? It's 5151. Yeah, 5150. Temple of Syrinx. What? So it's up. I think there's something hosed in the database. No. The fact that it was pixelating meant it knew it was bringing up the app. I think something got hosed in the Mongo database underneath. Oh, Mongo. I know. I can tell you internally on Slack every single. Oh, I shouldn't say that. I'm like, Postgres does JSON. Let me try to think about how I'm going to try to rescue this. What? No, I can't. You know how long it took? So I'll show you. I'll walk you through some of the code, and I'll tell you what you would have seen, and you'll imagine it. I'm not running anything else on Docker, but let's see if Docker, maybe it's down, you're right. Maybe let's just do Docker PS. Nope. They're all up. Restart Mongo? Sure. We got nothing but, yeah, we do. Do you want to see a little bit of the code, though, at least, just so you can understand, like, what's going on, rather than me troubleshooting Linux? And then we can talk about, I can try to get it to work? Okay, let's just do that. All right, so you would have imagined you saw a number that showed the brightness, and you see a grid of images? Yes. That code right here, it goes through for each image and calculates the brightness for each image, and then what you can do, imagine if you will, a carousel of images and then a selection on the left side. And you can pick the brightness field, and then you can filter based on the brightness value, and it'll interactively change the images that you can see. So it becomes very easy to see, these images are too bright. I want to delete them from my data set. That kind of stuff, okay? You can also do like a plot where you can show, that's enough for these ones. Let's get to the real stuff. This is not any, this is just basic OpenCV stuff. This is the interesting parts. So in this one, I'm calculating embeddings. So what's happening here is 51 comes with a model zoo. So I use those because those are just easier. We've taken a bunch of the most popular models and put them in a format that works really quickly inside of our platform, but you could do this with external models as well. This is too small. So what's happening here is, in this one, I'm loading the ResNet 18 model. This is probably one of the simplest computer vision models that does embeddings, okay? The next line is I'm loading OpenClip. Have any of you heard of OpenClip? The vision people should say yes. OpenClip is what's called a multimodal model. Do you know what multimodal means? Some people do. You want to explain it? Don't say multi-modes. That doesn't count. Multimodal in this case means it handles both text and images at the same time. That model was trained with images and captions for those images at the same time. And so it's doing LLM-like stuff with the text, and it's doing image-like stuff with the images, and it combines them together. So you can do things like ask it using text, show me all the images of, is this an image of a cat? And it will respond. Or give me a caption for this image. Some of them will give you a caption back out. All that kind of stuff. So that's a multimodal model. What's really great about a multimodal model, if you are going to get into computer vision, is you can use them as your first pass for doing image classification. What's the typical process when you do image classification and you're building one of these models? What do people spend millions and millions of dollars on every year? Annotations. You know, remember like Meta, all those poor people and I don't mean financially poor, I mean like I feel bad for them poor, like in Africa and stuff, who had to look at all the horrendous pictures on the internet and say safe, not safe, or I'm showing you like this is a knife, this is a gun, like that's annotation, right? These models, again, it's all about data. You can't just give it a picture. You're training the model, so you have to say, in this picture, here are the following things, or this is a safe image, or this is a porn image, or this is a whatever image. Someone has to go through and do all that stuff. Because the OpenClip model understands human text, and you knew you had a certain number of classes you wanted to classify for, let's just say you wanted to classify, give me some examples. Safe for work examples. Anyone? At work, think about what you do at work. Is there anything that you do with images at work where you'd want to have classes? Not safe what I do actually at work. What? Laptops? Yeah, so you could say, what model laptop is this? Right? If you can train, or you could say some laptop or a desktop. Yeah.
It's a vendor we recognize, it's not a vendor we recognize.
If the model's been trained on it. What I typically do is say, is this a cat? Is this a person? So you have a question, what is this a picture of? And then you give it an array of classes you want it to find, and it goes through the images using that text and generates that last layer of the neural network model to predict this is an image, this is a cat, this is a this is a that. It'll actually attach that. And why is that great? Because nobody has to look at the image to start with, and you've already got labels already put on the image. It's really onerous going through every single image and writing it by default. This is actually a good use of machine learning, right? It's the same reason I like LLMs, because I think they're a good text calculator. I want to write this thing, but the white page is scaring a lot out of me, and I don't want to write, here's the outline I want, give me a first draft. And it gives you the first draft, and then you can do stuff with it. And that's the same thing here. It can give you a first draft on your labels, and then you can proceed to correct them. So that's the really great part about these one-shot open ones. The other one is there's a new one-shot model that just came out from Apple, and I'm computing the embeddings using that. So here, this compute visualization actually says, it does two things. Compute visualization calculates the embedding, and then at the same time, also does that two-dimensional reduction. So what comes out at the end is there's a field where there's a brain key that says this is where it is in the database, and you can actually do the embedding visualization. So that's all it takes to calculate embeddings, which is why I said it's super simple. And this isn't really just on our platform. It's pretty simple in general to make embeddings, okay? The nice part here is it's just integrated and you can start. And then what comes out at the end of this is you have a 2D plot on one side with a whole bunch of dots in clusters. Some clustered well, some clustered not. And as you circle the clusters, the images change. And you notice this cluster is cats. This cluster is stars. This cluster is motorcycles. So you actually get to see where it's actually making what those embeddings correspond to in your images themselves. So what was exciting about this for me is I could find clusters that are like, oh yeah, I took a lot of pictures of monkeys. Like, I like those pictures of those monkeys. Oh, there's a really good one. You can also see when there's a lot of mixture. Oh, there's monkeys, and there's birds, and there's kids climbing in trees all in this picture, these pictures in this cluster. This model is not doing a good job of picking out the things I want. I should either retrain on different data or use a different architecture. Yeah?
So my understanding was embedding that it's going to tell you if there's a monkey in the picture. Where's the part where
It's not going to tell you if the...
the monkey is?
So that is a totally different question. So what we're doing here is classification. What you're talking about is what's called object detection. I have slides for that. Do you want me to keep going with a little bit? And I can get to it. Do you want me to keep going with the text for the code for a little bit? Or is this code, like showing this code, not exciting? Some people are like, this sucks. Other people are like, show me some more slides. Keep going a little bit. Okay, so that's it. That's all you have to do. What I did in this last one, which you can also do with embeddings and UMAP, is you can just concatenate embeddings together, right? They're just coordinates for that image. So you can actually take the ones that come out of ResNet, which has no multimodal, so it has no human concepts really in it. It's really just looking for features, and you can concatenate that embedding with the ones that come out of OpenClip. If I could have shown you this, OpenClip does really good at picking out stuff that correspond to what humans think of, and classifies them, puts them closer together because we gave that semantic text. You put the two together, you concatenate them, and then run UMAP on them, and you get the benefits of both. You start to see more structure and more semantic meaning in some of them. So that's what's happening in those last two. I'm calculating that two-dimensional reduction by putting those two embedding vectors together. So that's a fun, really actually interesting thing to play with. Yeah?
So how does it feel? I'm assuming that all these the model is trained on a specific dimension of image. What if your image input is a different dimension?
So the question was, the model probably assumes it's one dimension. There's a set dimension for the images, and what happens if you feed a bunch in? You don't. Basically, there's submodels that can handle multi-dimensions. Some, they're trained on, like, let's say a 224 by 224 or 336. You have to feed in a 224 or 336 by 336 image. And then under the hoods, it can handle that in one of two ways. If you don't, you can either just crop. So I'm taking the center, you don't get the rest of the stuff, or I'm gonna rescale your entire image down to that. So you can do it beforehand if you want to. Some of the models they may be trained on a certain size, but they can handle any size image going in. It's just what ends up happening is the bigger the image you put in, the slower it becomes, right? And the model probably won't be able to pick that stuff out because it wasn't trained on an image that big. It can't handle as much of that information. Yeah? So the question was, when you go from 200 dimensions, like in that embedding plot, down to 2, is accuracy reduced? Has to be. It's the same way, yes, it has to be. So the thing that you pick with the dimension reduction is, what are you trying to preserve as most? It's the same way when I like to talk about maps, because A, I'm a geo person, but B, because I think people have already encountered this. Like, we all remember how, like, the Mercator projection, the one where all the lines meet nice and square, and Greenland looks bigger than Africa, right? What that map projection, when it's going from 3 to 2, what it's trying to preserve is direction, right? Because all the lines of latitude and longitude meet at right angles, right? But there's other projections where you can say, I don't care about direction. I'm not trying to navigate with this. I'm trying to see retain area. And so you use a different projection formulation. So the same thing with here. So that's the reason why UMAP is kind of a better than the others. It's basically saying, hey, you want to keep like things near like things as we go down in dimensions, and I'm going to just try to statistically find the best way to do that. That's what UMAP is doing. But yes, you're giving up something because you have to. There's just no way to do it. The advantage is you can actually visualize it. It does the reducing dimensions. That's just for visualization purposes. It's not. I mean, you could use that two-dimensional vector afterwards, but I wouldn't. If you don't care about visualization, I really wouldn't do that dimension reduction, right? If you wanted, the reason you'd want a smaller vector coming out at the end is because you probably want it to be faster, right? You want it to, because the size of that vector coming out partially determines how long it takes. So like if you're running something on a phone, you don't want a 2,000 dimensional vector, you probably want like a 512. So you would just pick a model that only has a 512 output layer at the end, and a smaller model. Any other questions about that? We good? Okay, the next thing I was gonna show you, God, I can't believe this was such a cool demo too. Can we just check to make sure it just doesn't come up, huh? Oh! It was because of her question. You get the prize, all right? Yes, all right, so as I said, doubters, let me show you, I ran those 3 embeddings. So now what I can, do you care about the brightness filter thing? Nah, yes? Come see me afterwards. I want to show the embeddings because that's way cooler. All right, so remember I ran all those embeddings. I'm going to open these side by side. So the first one we said was ResNet. So there's all the dots for all our images in ResNet. Remember, ResNet doesn't have semantic knowledge. So what is this cluster right down here? Oh, some pictures I took in Kuala Lumpur when I was doing a show there. And these are all just pictures of me taking pictures out the window. What's this over here? Oh, these are things on a grass field. Now remember, ResNet basically does structured stuff. So I want to show you what happens differently though, because can everybody see that stuff well enough? Okay, so like this is me in Tasmania with some sort of parrot in a field. This is my dog doing lure coursing. Did any of you done lure coursing with your dogs? It's freaking amazing. It's so much fun. And then they tie a plastic bag to a rope on a field, which doesn't sound amazing, and then they hook it up to a lawnmower engine, and then they zip it around the field, and dogs who are like sight-focused and prey-focused run as fast as they can after that plastic bag, and it is the most amazing, if you like dogs, it is the most amazing thing to see. This is pictures of one of my son's field trips with a bunch of kids. How did the what?
How did you know that those were all connected to the photograph?
That's my guess. I'm just guessing. But that's one of the things the embeddings, like, I can circle that cluster, and I'm trying to say, okay, well, like, what connects that cluster? What might it be picking up on? It looks like it's like some sort of grass with maybe a little bit of light stuff on the top, maybe, but I'm mostly picking up on that I think it's grass. Like, here's a peacock, right? So we got a bunch of different things in the field. You'll notice what's happening. Can you see over on the right side? It's turning those dots orange, because I've selected them. Now watch what happens here. Let me pick a couple more, just to make sure that you see it. There's my dog, Hetty. She's so cute. And we'll pick a couple more kids. All right, there we go. Oh, no, there's Aya. This is the one that really likes chasing bags in the field. I changed that now. Remember, OpenClip was semantic, so it understands human concepts. And watch what happens to those dots. So those dots have now spread out, because OpenClip isn't caring as much about, is this grass in a field, what's the texture or the structure in the image. It's looking for things that are semantically related. So if I go over to this cluster over here, you can see this, it thinks are like tents in a field, or something else with like, it's some green and then a bunch of this white, like either a tent or a camper, some sort of camping thing. I don't exactly know. Embeddings don't tell you that information, right? They won't give you that. What's this? Oh, we lost all the other points. But so this is the difference between what I was trying to show you there was open, like a semantic model versus a structural model. The other thing that I'm going to point out here is that both of these models were trained on the same data set. They were both trained on ImageNet, so the data that went into them is what enables them to figure out the different features that's going on. If I had trained these models on just a car data set, same model, but just trained it on a car data set, these would look like a mess. Because I don't have very many cars in my pictures. 5 minutes? Damn it. All right, so, it would have been a mess. So this is where data is important. Don't just think about what model you're using. Really pay attention to whatever model and whatever data it was trained on. If the model's never seen that thing, it can't tell you about that thing. Does that make sense? Right? Okay, so can I just show you the really cool things? Is that fine? Okay. So here you were asking about, here's the zero shot. Remember I said I could just give it a list of names and it could tell me stuff? This is me telling, I think it was either the Apple model or one of the others, using the ImageNet classes. So ImageNet has like 1,000 classes in it. And I said, hey, take these classes and make one word per, tell me what you classify this into. And so it's making guesses. Let me clear this because it's not quite so exciting. It's making guesses about what's in here. So it says this is ImageNet does really well with birds for some reason. So it says this is a cuckold with 0.39%. It believes that with like a 0.39 probability, right? But then if I go to this one, it says this is a balloon. My daughter would be so insulted by this. She is not a balloon, right? But the other thing you can see about it is it doesn't really believe it's a balloon either, right? And this is one of the problems with LLMs, very quickly. We force LLMs to predict words no matter what the probability is it thinks of that word. And that's what a hallucination is. It predicts a very low probability word, puts it in the sentence, and because of the way LLMs work, all the words following it are based on that really word it never believed in the first place, and so it goes down this really weird path. Designers of LLM output should show us color coding for the probability of that word that it's predicting, so that we could say, oh, it didn't really believe that word. There's probably something wrong in this sentence. Done. Anything else? This is not a wedding. This is the prom, even though it says groom and bridegroom. This is a prom picture. That's my stepdaughter, and she would be horrified to think that she's getting married. And then that's object detection. Right, so this is a different model I ran, which is for object detection. So rather than saying the whole image is a groom image, it's now saying, I found the following things in the pictures, and here's what I think they are, with their probabilities. So it's pretty confident those are all people, which it should be. And then it also found the cell phone, which I was like, whoa, I didn't even think about that. So it found the cell phone in the picture. And so these are the differences between classification, which is the entire image, and object detection, which is a harder problem. Why? Look at what's happening. Look at the difference between the two things. It has to find a bounding box, and then it has to say, oh, I think this is a thing, and now I have to think about what is that thing that I actually found, right? So this is a harder problem, but it's way more useful. Like when I originally did this project, I wanted to do probability of filter out images with people because I never turn those into professional pictures. It's mostly just animals for me. And so what I would do, I did a classification, and it did poorly. One of my coworkers was like, well, Steve, you should have done an object detection, and if there's a high probability person in the picture at all, then just classify the image as people, right? Because it can actually go through and find people, as opposed to saying, here's an entire image, are there enough people in it to call it a people image, right? Which is a harder problem. Last thing I wanted to show, and this is related to the whole topic of the thing, is I did this. There's some other models that do text generation. Remember I said that they can generate captions and stuff? So there's, Janice, the new one from DeepSeek? Everybody heard of DeepSeek? Okay, they released a model. Yeah, even he's heard of Janice. That's awesome. Good for you. Or DeepSeek at least. They had released a model that actually can do caption generation as well for images. And then there's another one called Moonbeam. I forget who it's from. It's actually a better model. But I said, give me one word to describe this picture, and only one word, right? And I didn't have to give it a list of classes. I just said, give me a word, right? This one, I had to say, here's a list of classes, put it in one of these classes. This is just give me a word based on what you know, and what comes out of that is, we'll start with the good one, which is Moonbeam. That is the word cloud for my images, right? Because I said, give me one word, it associated that word, and it's 3 lines of clone to generate a word cloud. It's 150 lines of very complicated code to generate a word cloud, but I took it on for you guys, and that's what we got, all right? So this is what, thank you. I prefer the Moonbeam one also because these are really nice words. But you can see that like I was the photographer for my son's marching band, right? Like that's a nice big word there, serene, lots of people together for marching band. Nature, natural, joyful, of course, because it's me. Then we looked at the word cloud from Janice, and I have questions. Like, what does require mean in an image? So I can actually do this. I know I'm out of time, but give me one more second. So I can actually do this back in the interface over here. If I go to, let's clear that, I can say I'm going to make a histogram. And what I want to make it on is the Janice, where is it? Does anybody see Janice? Janice, image, answer. These are the answers that Janice gave me, right, for all the words. And I think this one was answering does not require reading text in the image. Band, I don't know where it came with require from. All right, so if I click on band though, like I want to see all the band pictures, I think that word cloud's busted. Anyway, if I click on band, that's why. Do you see the reason why? It's just the first 200 results. But if I click on band, it should, well, never mind. No, it doesn't. It should have clicked over and clicked all the images that were banned images on the other side. But if I can't do that, actually I can do it this way even easier. Forget the histogram. Where's the Janice images answer? Let's show them. And then let's say filter by Janice image answer. What was it, require? See, it doesn't say, it doesn't have it there. Reading though, what is that? These are all, that makes sense. These are all people reading, right? Some in synagogues, some camping, but those are the reading images, right? So this is, the reason I love this platform, despite the fact that it pays my mortgage and my food, is I love doing this stuff with images. Like I can't think of another way to do this with images. And so that's why I actually find this and it's open source, of course, right? And you can use it, and if you want to do it at a company, we have a Teams version that runs on Kubernetes and all that fun stuff. But I use it for this stuff, and I can play with all the latest stuff, and it's really easy for me to do things that would be almost impossible. I don't like matplotlib and in a Jupyter notebook and show me 5 images. Now show me another 5 images. Now show me another 5 images, right? Like I can easily scroll through and do all that kind of stuff. Finishing up the slides, if you want to, I had other stuff, but here's where I talk about different classification, object detection techniques. Here's where 51 fits in. Quickly, you define the sensor and the business questions, and then you go to production, and everything in between, we kind of tie that together with that kind of platform. Enough? No more sales pitchy? Yeah? Okay. Teams. Nobody needs another chatbot. Nobody needs another chatbot. That's the biggest thing. So start working with computer vision. People can you can make our customer lots of money and lots of really interesting problems, as opposed to, do I want to kill myself or not? There's interesting things you can do with just the phone. You don't have to go we have some data sets in there, but just take your phone photos. Like you understand those, you knew why you took them, you knew what's in them. Just start playing. Like that's the best way to learn this stuff, is to play, try out all the different models. Don't ignore your data. Don't ignore your data. Everybody gets all jazzed about the latest and greatest model, and it's not all that latest and greatest usually. It's the data that will give you a better impact. And I think this stuff is fun when it doesn't not start. Here's ways you can come hang out with me. This is the one I want you to do. Come join me on Discord, and you can hang out with us. And there's the link to the deck again, which also has the link to the repo. Move it on. Go back one slide. Oh, people were taking photos of this? Sorry. But you can take pictures of this, but what are you going to do with that? I mean, you can say, Steve thinks things are fun. Woohoo! Go to the deck, and then you can actually see all that stuff. And you can click on the link. But sure, thank you. Thanks, everybody. Sorry about the problems. And thanks for the Linux tutorial. Thank you for the Linux tutorial.